Yeah. Any question? So this is a set of equation that alpha and beta should satisfy, and we have to find the solution, right, of this equation. That what are the alpha and beta? But I'll explain why there is no unique choice, because there are infinite number of choices, and all of them are unitary equivalent. So if you can find by any way one particular choice, that is enough. All other choices are actually unitarily equivalent to each other, right? And you know that the physics doesn't change under unitary transformation, right? When you solve quantum mechanical equation, you can choose any basis for any particular operator. That operator may look like different operator in a different basis, but if these two bases are related by unitary transformation, then they describe equivalent physics. That's what we learned from quantum mechanics. And we'll also see that the various possible solution of this equation are actually unitarily equivalent to each other. So if you succeed to find at least one set of solution, all other solution will be unitarily equivalent. Okay. Maybe we'll not prove the. Okay, let me come to that and then I'll explain what do we mean by this statement. But certainly, the Pauli matrices, even if in two dimension, are not the unique choice, and even in the two dimension also, there is no choice actually. We cannot find all the alphas and betas in two dimension. Okay, so the statement that the Pauli matrices are the only choice in two dimension has two mistakes in this statement that we made. Is this is the only choice? So this is not the only choice, the Pauli matrices. And second, there is no, we cannot find all the alphas and betas in two dimensions. So in two dimensions, there is no solution at all. If you have any solution, then there might be many other solutions also in principle. But in two dimensions, you do not have any solution. We'll see that why. There could have been a solution for in two dimension, and I'll mention what is that. So let's start. I guess we have already 20 people. So, and if there is no more questions, so let's start from this. So what we trying to do is this. We're trying to find a Hamiltonian which is linear in P, right? So something like this form. And this is sometimes also known as Dirac Hamiltonian. Okay, it has this particular form. This is a relativistic Hamiltonian though. It doesn't look like this particular form. H is equal to square root of P square plus M square, or H square equal to P square plus M square, something like that. It doesn't look like this, but it has all the content of relativistic invariance. Okay, means if you square this Hamiltonian and use these properties, you will get this particular Hamiltonian, which has the correct energy momentum dispersion relation, means which has the correct form for of energy, right? Means E square will be P square plus M square. That's why it is still a relativistic Hamiltonian, but it's linear in P. Okay, so the point on the only thing that is left for us to find is some solution for this set of equation, right? So this Hamiltonian will be this Hamiltonian if the alpha beta that we have introduced, which is so far arbitrary, satisfy this set of equation, and these are called anti-commutation relation. These two and this and this one. So different alpha 1 and alpha 2 anti-commute with each other. because this will be 0 in that case. Alpha 2, alpha 3 anti-commute, alpha 3, alpha 1 anti-commute with each other. And if you put alpha I equal to j equal to 1, it will be twice alpha 1 square. And on this side you will get 2, because delta I not sound over, because I'm just substituting I equal to 1, I and j equal to 1. So delta 1 is just 1. So twice alpha 1 square is 2, so alpha 1 square is just 1, right? Means, by the way, I should also, means if this is matrix, I should put a identity matrix, right? Because on this side, delta ij is just simple matrix element of some 3 by 3 matrix, right? Delta ij. But each of these alpha i's are if they are matrix, means if alpha 1 is a matrix, alpha 2 is a matrix, their product is also matrix. So on this side, we have matrix, and if you put alpha, if you just simply replace this delta ij with I equal to 1, j equal to 2, this will be just simply 0. On this side you have matrix, on this side you have a 0, but you should also multiply the identity, so it will be actually a null matrix. Okay, so that is an identity matrix which should be there if these are matrices. At this level we don't know whether these are matrices or not. Okay, so in principle I could just simply write an identity. If these are matrices, then it will be an identity matrix. There should be identity matrix here. In fact, I can just put that maybe. So there is an identity matrix sitting here. Okay. I don't know the matrix. If these are matrix, then it will be identity matrix. If these are not matrix, then it will be something else. Okay. If these are simple numbers, then it will be simply number one. Okay. But it cannot be number, because numbers satisfy commutation relation. Two numbers commute with each other. So these cannot be number. So whether there are any other solution or not. So one possible solution that could be there is could be matrix solution. Okay. This is one of the convenient representation of this thing. So one more thing is that this property is the fundamental property or the defining properties of this alpha and beta. Okay. So if I say what is the definition of alpha beta, there is no definition. This is the only definition that we can have. Okay. This is the only place where we define them. The alpha beta should satisfy this relation. And in addition, so this is also for defining properties of alpha beta. And in addition, the Hermiticity of the Hamiltonian. So if your H is Hermitian, means H dagger is equal to H, then alpha I dagger should be also alpha I, and beta dagger should be also beta. So alpha beta should be also Hermitian, right? So these are mostly the fundamental properties of alpha beta matrices, and all other property that we can derive from this thing will be just simple corollary, not a fundamental. It's just a consequence of these things. Is that clear? For example, the trace property is actually a corollary of this thing. Means it's not a fundamental property; it's a consequence of all this equation. Okay. So what we discussed last time, the trace of alpha and trace of beta is 0. Right? We can just simply check how we did this last time. Also, there is another way of doing it. You can just simply compute trace of alpha I. Trace of alpha I should be just trace of alpha I multiplied by beta square. I just introduce this beta square because beta square is identity, so I can just insert a beta square there, and then I can just write this beta square as beta times beta, and then take one of these beta across this alpha I. So I just anti-commute this beta on this side. So there will be a minus sign because alpha and beta anti-commute. Okay. So alpha beta is equivalent to minus beta alpha I. Okay. The alpha I beta is equivalent to minus beta alpha I. So I use this anti-commutation relation here. So there is the minus sign. So this trace of alpha I then becomes minus trace of beta alpha I beta. And then you just use the cyclic property of the trace. So then it will be alpha I beta square. And beta square is again identity. So this is basically minus trace of alpha I. So trace of alpha I is equal to minus trace of alpha I. And then it's actually 0, right? So if something is equivalent, if x is equal to minus of x, the only solution it can have is what? 0, right? X equal to 0. So trace of alpha I is 0, and by similar argument you can check that trace of beta is also 0. So alpha beta are basically Hermitian traceless Hermitian matrices. Okay, and we need 4 such traceless Hermitian matrices: 3 alpha I and 1 beta. Why 3 alpha I? Because this is a vector. Means there is a vector index is there. It doesn't matter. We are not sure whether alpha is actually a vector or not. Right? One need to check that. How does alpha transform under rotation? P is certainly a vector, but there is no guarantee that alpha is a vector. Okay. So this is so alpha has 3 components that we can take, because P has 3 components. Basically, this is alpha I Pi. I should run from 1 to 3. So alpha has 3 components, and there is a beta there. So you should have 4 such quantity, alpha I and beta, 4 traceless Hermitian matrices which anti-commutes with each other. Right? Is this okay? By the way, this is visible, right?
Yes, sir.
So yeah. Now these 2 conditions, that alpha I square is identity and beta square is identity, and their trace is 0. These 2 conditions is enough to ensure to guarantee that these matrices at best be even dimensional, because alpha I square is identity means their eigenvalue are only plus minus 1. Any operator whose square is identity, it implies that its eigenvalues are simply plus minus 1. Okay. Now on top of that, you have this tracelessness condition, that these matrices are traceless also. So if the eigenvalues are plus 1 and minus 1, and if they are traceless, then how you can arrange these eigenvalues? It could be 1 plus 1. If you have 1 plus 1, you should have also 1 minus 1. So they should come in pair, right? If you are in odd dimension, you cannot do that. If you have 1, for example, if you're in 3 dimension, you can put 2 plus 1, 1 minus 1, or 1 plus 1, 2 minus 1. You cannot make the trace to be 0. Only in even dimension you can make it, right? You can have 2 plus, 1, 2 minus. If you are in a 4 dimension, it could be 4 plus and 4 minus, and so on. Okay. This can be ordered in any way, but the total number of plus 1 eigenvalues should be same as total number of minus 1 eigenvalues, and that ensures that the matrix representation of this thing should be even dimensional representation. Is that okay?
Yes.
So the lowest even dimensional representation that we can think of is the 2-dimensional representation, right? Is there anything?
So can you repeat the tracelessness argument that you just gave?
Just a minute. Is this chat box? Do you see any chat box here? Because I think you don't see that, right? Because is there anything that is obstructing the slide?
No, sir.
No, sir.
Okay, thank you. Because I just opened this thing to see the responses. Anyway, yeah, tracelessness is this matrices are traceless, right? That is okay, right, Shiva?
Yeah, the argument that you gave that they should be traceless. Can you please repeat that?
What I'm saying that some of the diagonal entries should be 0, right? This is the tracelessness. Now that property, the trace is 0, is also invariant. It's basis independent statement. Means if you go to a basis in which these matrices are diagonal, then also it should be traceless, right? So now the eigenvalues are plus minus 1. So how we can arrange in any arbitrary dimension these eigenvalues that you get it, the total, you get the trace to be 0, right? This you can only do in even dimension, right?
Yes, sir.
If you have plus 1 means if you have eigenvalues which is like plus 1 minus 1 or plus lambda minus lambda, and if you want that the sum of this eigenvalue, the diagonal entries should be 0, that means the trace should be 0, then you can only put this eigenvalue in pair, means lambda minus lambda, or lambda 1 minus lambda 1, lambda 2 minus lambda 2, and so on. Okay, so that means the eigenvalue should appear in pair. if your eigenvalues are plus minus lambda I in general, this is plus minus 1, but I am just talking about in any general, it may not be plus minus 1 always, right? So if your eigenvalues are plus minus lambda 1 minus lambda 1, lambda 2 minus lambda 2 and so on. So, and the trace is 0, then the eigenvalue appear in this way, means it should be pairwise appearance. Lambda 1 minus lambda 1, lambda 2 minus lambda 2 and so on. So they should appear in equal number. In this case, it's plus minus 1, so they should also appear in pair, right? To have your trace to be 0, and it doesn't matter in which, it should be in even dimension, but doesn't matter in what is the event dimension. It can be 2, 4, 6, whatever it is. But in odd dimension, you cannot do that. Means you can still have plus minus 1 eigenvalues, 2 plus 1 minus, these are plus minus 1 eigenvalues, right? Its square will be identity. And if you just take a matrix which looks like, let me see, let me just share this. Can you see this thing?
Yes, sir.
Let's consider a matrix of this kind. So it has 2 plus 1 eigen entries and 1 minus 1 entry. So the square of this matrix is also let's say this is a matrix A. Now A square will be identity. If you check.
Absolutely, yes.
Right? So the square of this matrix is identity. That doesn't mean that the eigenvalue appear in pair. The eigenvalue doesn't, one argument, if A square is identity, it eigenvalues are plus minus 1. That this doesn't ensure that the eigenvalues are, means, will appear in same number. Means there will be 1 plus 1 minus or 2 1, 2 plus 1 and 2 minus 1. It doesn't guarantee that. Eigenvalues are plus minus 1 means that it could have n number of, if it's n by n matrices, it means it can have k number of plus 1 entries and n minus k number of minus 1 entries. It just say that, and n can be even or odd. But if you want to have a traceless, in addition, if you put the trace of 8 equal to 0, then it should be even dimension. That's what I am saying. Is that okay?
Yes, sir. Yes.
The trace of A equal to 0 implies that A should have the even dimension representation, not this A even dimension. Okay. So let me go back. Okay. Lowest even dimension that we can think of is n equal to 2. Now, in 2 dimension, how many linearly independent traceless Hermitian matrices we can have? If you do not know the answer, traceless and Hermitian. At least, okay, let's ask this. In 2 dimension, means in 2 by 2 matrix space, how many Hermitian, in linearly independent Hermitian matrix we can have?
4 in 2 dimensions.
Or 2 dimensions, sorry? Someone was saying something?
4.
4 linearly independent Hermitian matrices, right? Yeah. So yeah, that's the correct statement. And if you put the traceless condition, you reduce the number by 1. So basically, it's actually 2 square minus 1. So there are 3 linearly independent traceless Hermitian matrices, and these are the Pauli matrices normally. Okay. It can be any linear combination of these matrices also. the general formula is actually in any dimension, it's n square minus 1. And I just leave it as an exercise for a general dimension. For n by n matrix, what are the number of linearly independent traceless Hermitian matrices? Okay, so you have to show that this is n square minus 1. And there is another part to that problem, so I'll also come to that. So in 2 dimensions, these are the simple sigma i's, 3 Pauli matrices, because the number of traceless Hermitian matrices are 3. But that doesn't say that we cannot find another 4th matrix, which is also traceless Hermitian, right? Means we have 3 linearly independent matrices for sure. Means these are sigma 1, sigma 2, and sigma.
Hello. This is similar to this. Think of that these alpha i's are basically the sigma i's.
Sir, may you please repeat, sir? You are not audible.
So your last statement
Hello?
was your voice just faded in and out. Your last statement.
Because of the network, just I got the message that the network is poor. What I'm saying, in 2 dimension, we have these 3 sigma i's, right? These Pauli matrices, sigma 1, sigma 2, and sigma 3, and they satisfy this relation. So just I can just simply think of that the sigma i's are basically my alpha i's, right? Because the alpha i's also satisfy the same relation, right? But I need another beta also, which also anticommute with the alphas. Sigma I is anticommute among each other. Alpha I is also anticommute among each other. So there is anticommutation relation. So I can just simply take the alpha I to be my sigma i's, and I need another betas also. So because beta is also a traceless Hermitian. You can say that okay, so we don't have any other linearly independent traceless Hermitian matrix. That's true. You have only 3 linearly independent traceless Hermitian matrix. But who said that that is the 4th traceless Hermitian matrix has to be linearly independent? Who said that? Right? I can just find another 2 by 2 traceless Hermitian matrix, which may not be linearly independent to sigma, but still it's a different matrix, traceless and Hermitian. Only thing I need to check is that it anticommutes with the sigmas, right? That's what I need to check. Is this statement clear?
Yes,
So
sir.
then that can be anything. I mean, it's not specific. Like,
Yeah, anyway, there is no specificness in alpha betas also. We'll see that. Why alpha betas are not also specific. Okay, there are many choices of alpha beta. We'll actually be accustomed to that later on. But anyway, the statement that I just made is this. There are many choices doesn't mean anyway that there is no choice, right? There is no choice and there are many choices, completely different statement. So what statement we are making right now, that there is this choice still, I guess. We need to see that, but there is no linearly independent choice. But this statement doesn't say that this has to be linearly independent. This only says that this should satisfy this relation, this alpha beta. To satisfy this relation, we'll see that it's equivalent to that. Okay. So what I'm saying is this: sigma i's are okay.
So your voice is not clear.
And the beta, let's just make this comment. So you know that.
no, sir, can you repeat the last statement? I mean, your voice, you are not audible.
Okay, so what I'm saying, we need 4 anti-commuting matrices. Right? In 2 dimension, I already have 4 anti-commuting matrices which are traceless and Hermitian, not necessarily linearly independent. Okay. In fact, linearly independent, but I'm not trying to make that statement right now. Okay, because what I need is actually 4 traceless Hermitian matrices which satisfy this condition. That's enough.
I should not put the linear independent criteria here because this is what I need. I need 4 traceless Hermitian matrices which satisfy this criteria. Okay. Forget about any linear independence of them. Whether they have to be linearly independent or not, that's a different question. We'll not go into that right now. Okay. So I need 4 traceless Hermitian matrices, and they should satisfy this condition. Okay. Any 4 traceless Hermitian matrices will not do the job because I need to satisfy this condition. The solution. Okay. Now in 2 dimension, I know that there are 3 linearly independent traceless Hermitian matrices. There exist 3 linearly independent, but there can be more traceless Hermitian matrices, which may not be linearly independent to each other, but in general there can be more traceless Hermitian matrices. So let's see that means so 3 of them which are linearly independent, which we can definitely take because they are anyway linearly independent. The sigma i's which satisfy this relation. So I can take my alpha I to be this thing, this sigma i's itself. Now the job is will be done if I can find a beta in 2 dimension, which is traceless, Hermitian, and which also anti-commutes with the alphas. And my alphas are actually sigma here. So if I can find another traceless Hermitian matrix, which is not sigma i's itself, something else, and which also anti-commute with the sigmas, then I am done. Right? So this is the statement. If I can find, so I have to find a beta. The 4th traceless Hermitian matrix I have to find. Is this okay? Means I'm just pausing the question. I have to find a beta. This alpha i's are actually the sigma i's. Now what I want, I have to find a beta, and I'm just trying to see whether I can find a beta in 2 dimension or not. That is the question. Is this okay?
Sir, does the linear independence of sigmas have any significance here?
On what? Means sigmas are linearly independent, but in significance means?
I mean, we don't need they to be these alphas to be linearly independent, but we are getting a linear independence here. So does this
No, I'm saying that. So I need 3 quantities, right? So what does linearly independence does actually that you are not actually taking the same matrix and working. So all of the alpha is the same or not? How do you distinguish that? First of all, how do you guarantee that? So one possible way of guaranteeing that is that just to take linearly independent matrices, right?
Yes,
so you don't bother that your alpha 1 and alpha 2 are actually 2 distinct matrices or not. You have to ensure that, right? So one possible way is you have 3 linearly independent matrices, so better take them, right?
Yes.
By this way, you actually ruled out any possible any possibility that one of these alpha 1 and alpha 2 may be same thing. You already put them to the same. Means it's just a multiple 2 times of the first matrix. Okay. Means if you have one, for example, let's say you take sigma 1, and then in the alpha 2, so alpha 1 is your sigma 1, and alpha 2 is, let's say, 2 times sigma 1. Then they will not anti-commute, right? They are, both of them are traceless, Hermitian, but they will not anti-commute because one is sigma 1, another is twice sigma 1, and sigma 1 doesn't anti-commute, right?
Okay, sir.
So we need 2 traceless Hermitian matrices or 3 traceless Hermitian matrices for the alphas, but they should also anti-commute. So one best way to do that is actually to take the sigmas itself, because the sigmas anti-commute with each other. Forget about their linear independence. The sigmas anti-commute. So you are guaranteed to have at least solution for the alphas, right? In 2 dimension. If you take these alphas to be your sigmas. Is this okay?
So the simplest solution one can have for this for these criteria that we have just said in 2 dimension at least, it's to have polymatrices as our alphas, right?
Yes, this is one of the solutions, right? And this is guaranteed to be traceless, Hermitian, and this is guaranteed to satisfy this relation, right? Because we already know that the sigma satisfies this relation, right?
Exactly. So, but we can also have other relations.
Sorry.
But we can also have other matrices that are linear combinations
Yeah.
of are polymatrices that
Exactly,
can satisfy
exactly,
this.
exactly. In principle, yes. In principle, yes. There will be traceless Hermitian, but we need to check whether all of them anti-commute or not. If you can find, then
Exactly.
it's then also you're done, right?
Yeah. But the simplest relation that we can think of is of polymatrices being the alphas.
Yes,
Okay.
yes, yes. Yes. In fact, what you can see, it will be clear in a moment. What you can actually choose is the Pauli matrices, or there are any multiple of them. Okay, means if you take your alpha 1 to be sigma 1 or some number multiplied by sigma 1, that's why that is the only choice you have actually, nothing else. Okay, so it will be clear. So what I'm saying for the moment, the simplest or the safest choice you can make for the alpha i's is the sigma. Means you take the sigma matrices itself as your alpha matrices. Okay, whether you can have other choices or not, we'll come back to that question. But for the moment, what I need is some solution, at least one solution. So for the alphas, this is the solution, but I have to find another matrix, traceless Hermitian matrix, which will anti-commute with the alpha. Okay, so I have to find that. Means I have to find the beta also. The question is whether we can find a beta or not. So let's just see that. Okay. So you, by the way, how many basis vector you need in 2 by 2 matrix space?
Two, right?
Do you know that? Just like in 3 dimension, if you want to write a vector R, you need 3 basis vector, right? X hat, Y hat, Z hat, right? Z hat. So you can write any vector which has 3 components in a linear combination in terms of this basis vector, right? In the matrix space also, since the matrix also actually equivalent to vectors, right? They have all the properties of a vector. So any arbitrary matrix can also be written in terms of the basis vectors. Okay. So in 2 dimension, there are some basis vector. So any arbitrary 2 by 2 matrix can be written in terms of that basis vector. So do you know what are these basis vector in 2 dimension? Or how many basis vectors are there in 2 dimension?
Four, I think.
4. These are basically these natural bases, right? Let me just share this thing. Yeah. So if you, so the basis vector in 2 dimension is basically this natural basis 1, 0, 0. These are 4 in number. 0, 1, 0, 0. 0, 0, 1, 0, and 0. These are the 4 basis vector. These are called natural bases in matrix space, and these are the natural basis for 2 by 2 matrix space. So any matrix, any arbitrary 2 by 2 matrix M with, say, general arbitrary 2 by 2 matrix can look like this one, right? A, B, C, D. If it's a real matrix, if it's a complex matrix, then the entries will be complex. This is an arbitrary 2 by 2 matrix, right? You can write this any arbitrary 2 by 2 matrix in terms of this basis vector, right? It will be simply, your aim will be simply, if I call them to be, let me give them some number, some name maybe. Anyway, so let me write it in this way. So it will be something like this. So this is what you call writing a matrix in terms of its basis vector. So this is the thing. I'm not writing the zeros. B times 1, all other entries are 0 in this matrix. C times plus D times this. Right?
Just like you write a non three-dimensional vector r vector as x time I cap plus y time j cap plus z time k cap, some exactly similar to that. So there will be d here. Okay. So these four are actually the basis vector. This span the basis of 2 by 2 matrix space, and they are linearly independent also. You can check. Okay. But these are not the only four basis vector in 2 by 2 matrix space. Just like I cap, j cap, and k cap are not the only three basis vector, right? There are infinite many choices. Any linear combination of of them will be also a basis vector. Similarly, here also, any linear combination of this natural basis vector is also a basis vector. And one such linear combination is this Pauli matrices. Yeah. So so unit 4. So in 2 by 2 matrix space, if you include the identity and the sigma i's, so identity sigma 1, sigma 2, and sigma 3, these four. So these are the Hermitian matrices, and these three are traceless Hermitian matrices. Identity is not traceless. Identity has trace 2. So if you include identity with these sigmas, so there are 4 matrices. Okay. So these 4 matrices, these are actually, you can check some linear combination of the natural bases. Okay. And so if you, the natural basis vector that I just written there actually, so you can just check these matrices are some linear combination of those natural basis vectors. So in fact, these are also, you can also take them to be the basis vector. So they also span the basis for the 2 by 2 matrix space. Okay. So there is a possible way to check this thing also, that you can see that you can check that they are linearly independent and so on. Okay. So they can be also used as a basis vector to write any arbitrary matrix in 2 dimension as a linear combination of them. Just like we wrote the M matrix as a linear combination of the natural basis vector, we can also write any 2 by 2 matrix in 2 dimension as a linear combination of these 4 matrices. Okay. In fact, you can just simply check it for any simple example. Just for example, the matrix that is considered ABC, you can write it using this thing, this object in principle. And this is a generic statement. This is just statement in 2 dimension, but this can be made general. You can, so this is left as an exercise. So in any arbitrary dimension, means n dimension, so there are n square minus 1 traceless Hermitian matrices. If you add the identity to it, you will have n square matrices, Hermitian matrices, right? One of them is Hermitian but not traceless, but remaining n square minus 1 is traceless. In total, there are n square matrices. N square minus 1 traceless Hermitian matrices plus 1 identity, so that means there are n square matrices. Okay. And in n dimension, you need n square basis vector. Okay. And these are this basis vector. Okay. So any arbitrary matrix in n dimension can be expanded in terms of this basis vector in this way. Okay. So this is any hello.
Yes, you are audible now. You just faded out for a second there.
What I'm saying, have you seen this relation that any 2 by 2 matrix can be written in this way?
No, sir.
No. Okay. Okay. So when you will be doing this exercise, I guess it will be clear. And so we will discuss that in the tutorial, perhaps. So in the meantime, what you can try to write down this 2 by 2 matrix A, B, C, D in this way, means using this 4 matrix. Okay. How it can be written in terms of using natural basis vector, I just wrote it in the whiteboard. But you can just try writing the same thing using this basis vector. Okay. And you can also try to check that they are linearly independent and so on. And so either you do it for 2 by 2 or n by n. N by n is left as an exercise. You can just check that. So this is true for in in any dimension. If you just take into account all the traceless admission matrix and the identity matrix, they can be taken as the basis vector. Means any arbitrary matrix you can write in terms of this basis vector with multiplying some coefficient. Okay, so these are some coefficient. For example, in this case, I guess this should be so this a coefficient you have to find. Given the matrix, this coefficient is determined. Okay, can be determined. Okay, so so if I want to write down any arbitrary traceless Hermitian matrix, let's say in this case, we might do any arbitrary, not necessarily traceless. Okay. Or Hermitian. It depends on if M is Hermitian, because identity and if M is the only mean that 0 and AI are real, then it will get. If your A0 and AI, if this coefficient are real, then M will be Hermitian, right? So what is the condition that means what is the expansion? Similar expansion. This is for any arbitrary matrix. But if I say that M is a traceless Hermitian matrix, then how does the right hand side look like? Okay, so let me do that. Share this.
So just the two poly matrices, right? Other two, one of the poly matrices and the identity one will cancel each other out. So there won't be any diagonal terms, just off diagonal terms, because we
no,
need,
only the identity, right? Only the identity will not be there. So any arbitrary 2 by 2 matrix you can write in this way: A0 times identity plus A1 times sigma 1 plus A2 times sigma 2 plus A3 you see, any arbitrary 2 by 2 matrix have 4 entries, right? Any arbitrary 2 by 2 matrix has 4 entries, 4 arbitrary entries. This can be complex or real, right? It was like A, B, C, D, something like that. This is any arbitrary 2 by 2 matrix, right? If it's a complex matrix, then ABCD are complex. If it's a real matrix, then ABCDs are real. Now, what is this matrix, for example? If you just break it in terms of the matrices, means if you just explicitly substitute the matrices, identity matrix, sigma matrix, and all these things, it will look like this. M will look like A0 plus A3 and A1 minus IA2. I just normally forget whether it's minus I or plus I. Sigma 2 is 0 minus I, I0, or sigma 2 is 0 plus I0.
So minus I.
Minus I. Then this should be minus A1 plus IA2. So this is the meaning of this equation, right? And A0 minus A3. Right? So this is your aim. Means any arbitrary matrix, if you write it in this way, this is how it looks like, right? Now, if I give you that my aim is actually ABCD, not like something like this. So what is that correspondence? And ABCD is all of them are real. What you should do? You should just equate this, that A is your A0 plus A3, B is just simply A1 because A2 has to be 0 because A2 has a imaginary part, right? Means you can just, what you can do, just B equal to this, C equal to this thing, and D equal to this thing. Now you impose the reality condition and then solve this thing. You will see that your A2 has to be 0, and A is just A0 plus A3, and D is A0 minus A3. Right? C is C and B. You have to actually I don't know how we should do that. A1 minus A1 minus A1 minus IA2 and A.
Won't B and
Okay,
C
yeah,
be
sorry.
same?
Yeah. So in general, these are complex entries also. So only the real imaginary part of A2 can contribute here, right? And not the real part. If you take your A0, A1, A2, A3, all of them to be complex, right here, and then if I ask you, so this is any general arbitrary 2 by 2 matrix, complex or real, whatever, it doesn't matter. So all of these entries are, let's say, complex. Now, if I just give you this matrix and ask you what is the solution for A0, A1, A2, A3, you'll find some of the component will be 0 because all this thing has both complex and all these entries are complex. They have both real and imaginary part. Some of these entry will be anyway 0 because this matrix is a real matrix. And what you will find here, you'll find a complex matrix completely, right? And if you equate the component, you see there are 4 parameters here. If it's a complex, there are 8 parameters, right? And in this case, there are 4 parameters, and all the imaginary component here actually 0. So basically, you have 8 equation to solve for 8 parameters here, right? And you can in principle solve this equation. Is this okay? I can try to do it for this particular case, or you can just I can just leave it up to you to just, so given this thing, find what is your or maybe just use a different notation, A B C D, or here also you have A B, but these are A0, A1, A2, A3, and this is simply A, doesn't matter. Okay, this confusion can be removed. So this equation means this thing, and what I am claiming that any arbitrary matrix, any arbitrary 2 by 2 matrix, complex or real, can be expressed in this way, right? This is a one particular representation of that. Means it's actually arbitrary matrix, and it's an arbitrary complex matrix if your parameters are complex, or right. And now if I just provide you any matrix, for example this matrix, you can just solve for this coefficient A0, A1, A2, A3 from equating the elements of this with that, means with this matrix. Okay, this is normally the technique to do this thing. But my task is completely different. What I want, so any matrix, arbitrary matrix, can be written in this way. But what I want, a traceless Hermitian matrix. Okay, so that's what I need. So let's say I need a beta, right, which is Hermitian and traceless. So if my beta is Hermitian, then this entries has to be real. A0, A1, A2, A3, all of them has to be real, right? Is this clear why it has to be real? M is Hermitian, that means M dagger equal to M. M dagger equal to M, this implies all A0, A1, just a minute. Yeah, I think that one. So all this has to be real. Is this clear that why this has to be real? Because we take dagger of this, I dagger is I, sigma 1 dagger is sigma 1 because these are Hermitian, sigma 2 dagger is sigma 2, and sigma 3 dagger is sigma 3. So if this A0, A1, A2, A3, if under Hermitian adjoint, they remain itself, then M dagger will be simply M, right? But if they are complex, then you will find some star here, and M dagger will not be M. So M dagger is M, means hermiticity of M imposes that this has to be real coefficient. Okay. And if you impose tracelessness, if trace of M equal to 0, then what is the consequence of this condition? Shivam was saying that A0 and A1 has to be A0 and A3 has to be 0.
Or equal.
Just A0. Just A0 has to be 0.
This condition, trace of M, if you take trace of M on both sides, trace of M will be just trace of identity, trace of sigma, trace of sigma 1, trace of sigma 2, and trace of sigma 3. But trace of all these matrices are 0 because they are traceless already. So trace of M is equal to A0 times trace of identity, right? So now if you trace of identity is not 0. So if your trace of M is 0, then only thing is required is A0 is 0, right? Is this okay? So any traceless Hermitian matrix M, which is traceless, oh, traceless. This can be written in this way. Simply as hello.
Hello?
Hello, can you hear me?
Yes, sir.
Yes, now we can.
Yes, sir.
Okay. Can you see this thing again?
Sir, you can turn off your camera.
Sorry. Why is that? No, the camera is on. I don't know. Is it visible, this thing? Anything is visible from my desktop?
Yes, sir.
Sorry?
Sir, AM is traceless and Hermitian. This slide is visible.
Okay, thank you. So if any arbitrary traceless Hermitian matrix is given, then I can simply write in this way. Okay, AI sigma. Any arbitrary matrix can be written as A0 identity plus AI sigma sum over I. But if it is a Hermitian and traceless matrix, for example, my beta, which is traceless Hermitian, right? So I can write my beta in this way. AI sigma. I can write in this way. Let me change the connection. So given I have 3 alpha matrices, which are my sigma matrices, means which I assume that these are my sigma matrices in 2 dimension. All of you are there, means I am connected to you.
Yeah.
Yes,
Okay.
Sir, maybe
So I
turning
guess,
off your hello.
yeah.
Maybe turning off your video will help the bandwidth actually.
Okay, okay, yeah. So if I assume this that my alpha I, 3 of the alpha is my sigma itself, what I want to find is the fourth one, the beta I want to find, which is Hermitian and traceless in 2 dimension. Now in 2 dimension, any Hermitian which need not anti-commute with alpha, I don't know whether it will anti-commute or not, can be written in this way. Okay. So what is the right? If I find some solution for that, then I am done. Okay. So then I can say that there exists a beta at least, which is some AI multiplied by sigma I, and I have this alpha I, 3 alpha I, so I got four matrices, and so I got the solution. Okay. So let's check, because this is for any arbitrary traceless Hermitian matrix into 2 by 2 matrix space. Okay. So this is the most generic matrix.
It's 4 o'clock.
This is the most generic 2 by 2 traceless Hermitian matrix. And let's just try to see what happens if I just find this thing and the anti-commutation relation. Okay, so let me just write this: beta alpha I. So I have to verify that this is 0, right? Or what is the condition that AI should satisfy so that this is 0? Alpha, let me just write alpha j plus alpha j beta this has to be 0, right? If I can show that that there exist some choices of AI for which beta will anti-commute with this alpha, then there exists a solution. Some non-trivial AIs, okay, if I can find. And if I cannot find any AI which will satisfy this, then I will say that I can only have at best 3 alphas and there exists no beta in 2 dimension. Okay. So I have to find some solution of AIs, so that this is equal to 0, because beta and alpha, they anti-commute. So this should be 0. Now what is my beta? My beta is actually AI sigma I. So let me just substitute that, sum over I, AI sigma I then I have a sigma j, yes, sigma j, because alpha j is basically sigma j, plus sigma j I sigma. Right. Now you can take the sum. You can also take AI common. I am not writing sum over AI specifically. I am just taking this AI common. What is here? Yes. Yes. Hello.
So we are not.
Just a minute. Just a minute. Let me. Hello. Can you hear clearly?
Yes. Now.
Okay. So let me just repeat this thing. So in 2-dimension, I have already 3 traceless Hermitian matrices. So I just took them to be sigma i's, okay? Because I know these are traceless Hermitian, okay? And also I don't have to bother about whether they will anti-commute or not, because I already know they anti-commute. Traceless Hermitian matrix and this sigma i's anti-commute with each other. So I just take them to be my alpha i's, okay? And now I am trying to construct another traceless Hermitian matrix in 2-dimension. And any traceless Hermitian matrix in 2-dimension can be written in this way. Any arbitrary traceless Hermitian matrix in 2-dimension can be written in this way. Okay, where the sigma i's are the Pauli matrices and ai are the coefficient. Okay. Now I took my beta to be this sum over I ai sigma I. Now what I have to show is that if in order that this beta, because this beta cannot be any arbitrary traceless Hermitian matrix, this beta has to anti-commute with the alpha I. So what is the restriction that I can find from that on AIs, right? Any traceless or arbitrary traceless Hermitian matrix will not do this job. Maybe a particular beta will do this job. And so what is the restriction on AI? That this is satisfied, that this is 0, right? Now what I can find if I compute this, my beta is sum over ai sigma I just substituted them, and alpha j is just sigma j. And then I just took this sum over I ai common. It is actually sigma I, then sigma j, then sigma j, and sigma I. So what is this thing inside the bracket?
2 delta I.
Twice delta I, right? Very good. So this is twice delta I. So what do you get on this side then? Because you have a delta function, you have a summation, 2ai, right? Or aj, whatever it is. Twice aj. So if you try to check this, beta alpha j plus alpha j beta. If you want to check this, you will get, what is the answer you will get? You will get twice aj. Now if you try to check the anti-commutational relation of beta with alpha 1, you will get twice a1, and that will be 0 if your a1 is 0. If you try to check the anti-commutational relation of beta with alpha 2, you will get twice a2, and that will be 0 if a2 is 0. Similarly, if you try to check the anti-commutational relation of beta with alpha 3, you will get twice a3, and that will be 0 only if a3 is 0, right? So all the a1, a2, a3 are 0, so beta is 0. So there exists no non-trivial traceless Hermitian matrix that satisfies this relation, right? So this, if your beta is 0, this is 0 then, because beta times any matrix is 0 plus alpha times any matrix times beta is also 0. But is there a non-zero solution that gives non-zero solution which is traceless and Hermitian that also satisfies this relation to be 0? It's not. There is no matrix, no other traceless Hermitian matrix that you can construct out of using these sigma i's, because they are the basis vector. So you can write down any traceless Hermitian matrix using them. But you can see that the commutation relation of this beta, or the anti-commutation relation of this beta with the alpha I will be 0 if and only if all these AIs are 0. That means if it is null matrix. And we are not interested in a null matrix. We are interested in some matrix which is just traceless Hermitian, not necessarily a null matrix. Okay, some non-zero matrix, because beta square is identity. Beta square is not 0. So we cannot have any solution in 2-dimension, right? Because in 2-dimension you can only have 3 linearly
independent traceless admission matrix. All other traceless admission matrices are linearly dependent to each other, and they do not satisfy anti-commutation relation. That's the problem. Okay, this is the importance. Why the linearly independent things are actually coming into the picture. It is coming into the picture in this way because they should anti-commute. Okay. The problem is this: the anti-commutation and the linear independence is kind of seems to be equivalent. This is particularly true because we have only three traceless admission matrices in 2 dimension which are linearly independent to each other. Okay, but if you are in a higher dimension, where you have more traceless admission matrices which are linearly independent also, then this problem will not arise. Actually, means what I mean actually, this problem is that it seems that they are not linearly independent. That's why I am not getting this thing. It's true in a sense that because you have only three linearly independent matrices and you took all of them already, right? Is that clear? Hello?
Yes, sir.
Yeah. So just to conclude is make the conclusion for this thing is this: you take the 3 alpha i's to be your sigma i's or any linear combination of them, okay, such that they satisfy anti-commutation relation. So you should do that first of all. Now once you do that, you can try to find the 4th one by making another linear combination of the sigma i's, and now you should try to find whether they satisfy any the 4th one satisfy the anti-commutation relation, desired anti-commutation relation with the alpha i's or not. You will check it will only satisfy if all the coefficient is 0. Otherwise, it's not possible. Okay. That means there exists no 4th solution, which is consistent with the anti-commutation relation. That's the conclusion. So there exists no. I cannot find the 4 traceless admission matrices which all of them will satisfy among themselves. That hope is to go to next higher event dimension, and this is dimension 4. Okay, so let me come to that. Where is that? Yeah. Okay. So this formula will be very useful also in your in future part of this course, or I guess in various other courses also. It's a very powerful formula, and in fact this is also very useful. This is true for general n by n matrix, but you should do this exercise. Okay, I did it here. This alpha I beta anti-commutation is just twice AI, and it's not 0. It will be only 0 if all of your AIs are 0. Okay, this is what just I did now. Now in n dimension, in 4 dimension, how many traceless admission matrices we can have? Independent traceless admission matrices, n square minus 1. So n is 4. That means 4 square minus 1 is 15. Okay, so we can have 15. So there are a lot of choices. Okay, whether all of them anti-commute or not, that we need to check. But the point is, there exists 15 linearly independent traceless admission matrices at least. So I can take any 4 of them and then just check whether they anti-commute or not with each other. Okay. So we'll come back to this full set. What are these 15 traceless admission matrices we can have in 4 dimension, because they form the basis, right? Together with the identity. If you add to these 15 matrices the identity matrix, then you have 16 matrices in 4 dimension, and this 16 matrix should span the basis of 4 by 4 matrix space. And what are these 16 matrices? In fact, we'll see that in this course. Okay, so we'll come to that point. Right now, it is not our priority to find all of them. Okay. One more thing I have to just discuss, and then I'll come back here. Okay. Let's just do this. Okay. So we have in anyway 15 traceless Hermitian matrix in 4 dimensions. So what are these? I don't know actually, but let's try to at least construct this alpha as a beta and then check whether this is consistent in with the commutation anti-commutation relation or not. So one thing is this alpha I and beta, they anti-commute with each other, right? All of them anti-commute with each other. So they cannot be, so you know two matrices can be simultaneously diagonalized in the same basis if they commute with each other. But in this case, these 4 matrices, 3 alpha I and 1 beta, they anti-commute with each other, so they are not simultaneously diagonalized in same basis, right? But what I can do, I can take one of them to be diagonalized, right? So I will choose a basis in which out of these 4, one of them is diagonalized. You can ask why you can do that, how we can do that. The point is, what I am saying again, that there is no unique choice. And I will show this in a moment, why there is no unique choice. If there is a unique choice, then you can find something, right? There will be some way to pin down that unique choice. But if there is no unique choice, then the best thing you can do is trial and error, okay? Because there is no way you can fix it, because the choice is not unique. So one possible way just is this. I will choose the basis to be the basis in which one of this matrix is diagonal out of this 4. And a possible way is actually, I can means one possibility, and I'll give you another possibility, okay? That beta is diagonal. I'll just take that. So I'll work in a basis in which beta is diagonal. That means the other matrices, alpha i's will not be diagonal in this basis. So what is this, in this diagonal basis, how does beta look like? Now, beta square has to be identity. So the elements of beta can be at best plus minus 1. And it's a 4 by 4 matrix, because I am working in 4 dimension. And it has to be traceless. So how does this traceless Hermitian 4 by 4 matrix looks like, which is also diagonal and whose eigenvalues are plus minus 1? It simply looks like this, right? Beta equal to diagonal of plus 1, minus 1, minus 1. You could have interchanged this order, but this is most convenient way you can write it. In a matrix form, this looks like this. Beta is just simply identity, 2 by 2 identity matrix, then 0, then another 0, then minus another 2 by 2 identity matrix. You can square this matrix, you will get identity, this traceless, and it is Hermitian also, because dagger of any identity matrix is again identity matrix. So this is traceless Hermitian, and it has eigenvalue plus minus 1. So this is the choice of beta that I can make. So I can go to a basis in principle in which beta is diagonal. So this is my beta. Now I should take the alpha to be off diagonal, right? Because alpha beta cannot be simultaneously diagonalizable. Is this point clear? Hello?
Yes.
For whom it is not clear? Okay, it seems it's clear to all of you. Now, I have to find alpha such that it's Hermitian and it's traceless, it's not diagonal, and it satisfies the anti-commutation relation. Alpha I, alpha j plus alpha j, alpha I is twice delta ij, right? It's a quick guess, means just a guess. It's just to take, is just to use the knowledge of 2 dimension that we have already have. In 2 by 2 matrix space, we know that the sigma matrices anti-commutes with each other, and they are traceless and Hermitian. So what I can do, I can just take that sigma matrices itself and just arrange in this way, not in a diagonal block. You can also do the diagonal arrangement also, means you can put the sigma I here and sigma I here with a minus sign, but then your beta has to be different. Beta cannot be diagonal, but if I took my beta to be diagonal, what I can do, I can just put the sigma i's to be off diagonal, okay, and the diagonal elements are 0, and you can check this is Hermitian. This is one possible matrix I can construct, right, which is Hermitian because sigma i's are Hermitian. Its diagonal elements are 0, so it is traceless. Now, only thing that I have to check that it satisfies the anti-commutation relation. And it's very trivial to check that this satisfies the anti-commutation relation because sigma I also satisfies the anti-commutation relation, right? So we can explicitly check that. So I am taking my alpha I to be just this thing. And then you can ask me how we can find this solution. In fact, I didn't find this solution. This is Dirac who find this solution. But it's not difficult to find either. It means it's not difficult to guess either. By the way, there is a little bit of involved way of further arguing what should be the closely the form of this alpha i's, but it doesn't give you. I can go through that argument sometimes else, maybe not today, but it doesn't help too much because the reason will be clear in a moment, because there is no unique choice for these alphas or betas. Okay, there are infinitely many choices. So if you can make one particular choice which is consistent with the relation, then you are done. Okay. So this is your alpha I. So let's check whether alpha I and alpha j satisfy this anti-commutation relation or not. Whether this is twice delta ij or not. Plus alpha j alpha I. Right? So I have to check this. So this means I have a 0, I have a sigma I, sigma I here, and the 0, times 0 sigma j plus similar stuff, okay, which I have not tried. Sigma j, alpha j and alpha I. Okay. Let's check this. What is this? What is this product, by the way? Quickly, anyone? So let's do this.
Delta is
This product.
delta
product
I
of this
is 0.
first entry,
Delta I delta
sigma I, sigma j,
sorry.
right? The first entry is 0 multiplied by 0 and sigma I multiplied by sigma j, right? 0 times 0 is 0 plus sigma I times sigma j is sigma I, sigma j, right? So this is the first entry. Then the next entry here is 0.
Off diagonal terms will be 0 and the diagonal terms will be sigma I,
Right.
sigma
Off
j,
diagonal term
sigma
will
j.
be 0. Diagonal term will be just product of these two. So this is 0 multiplied by this is also 0, and the again diagonal term here will be sigma I, sigma j. Okay. So this is what you got here, and if you do this, here sigma j is the first entry, means alpha j is there, that means sigma j is here, sigma j is here, and sigma I is here, and sigma I is here. It will be just in opposite order, means it's just an interchange of these two here. Okay. Basically, this is your this thing, and this is your sigma j. It will be just same thing in opposite order. Sigma j, sigma I. Times 0 here, and this is sigma j, sigma I. And if you add these two, what you will get? If you add these two, you will get this thing, a diagonal matrix which looks like this. Sigma I, sigma j plus sigma j, sigma I. This is nothing but twice delta ij, right? Because sigma matrices satisfy this anti-commutation relation. That's why I took this sigma matrices. In the last diagonal entry is sigma I, sigma j plus sigma j, sigma I. This is also twice delta ij. And if you can take this twice delta ij common, so then this relation will be twice delta ij times identity, right? So this choice does the job. Is this okay?
Yes, sir.
This choice that I have made, the beta diagonal with identity 0, 0 minus identity, and alpha I to be this, does the job. Only thing maybe you can check whether the alpha and beta anti-commutes or not. That I can leave it up to you. Okay, you can check that this is also true. Means this alpha I and the beta that I defined also anti-commute with each other. Okay, and these are the alpha that also anti-commute with each other. They satisfy the same relation. That is we need to ensure that they anti-commute for different I and j, and gives you alpha I square equal to 1 for I equal to j. Okay. So we found a solution in 4th dimension. Okay. So the beta is traceless Hermitian. They anti-commute with alpha I. That you can check in 1 step or 2 step. These alpha I, these are also traceless and Hermitian, and they also anti-commute with each other. Okay. So we are done. And the square, if you square this thing, you will find that their square is also identity. Okay. So we found the solution. Okay, and this is one particular representation of this alpha beta. There are infinitely many possible choices for alpha beta, and this particular
Just resume it.
so
Okay.
this network problem is constant thing that we will be facing throughout this course, I think. Yeah. So this is just to explain why there is the unique choice, and the various choices are equivalent to each other, means unitarily equivalent to each other. Okay. Let me just explain why. So let's suppose I have some alpha I, means 3 set of alpha I which satisfy this relation, alpha I alpha j plus alpha j alpha I equal to twice delta j. So let's assume that I have found some solution. Just for example, in this case, I found 3 alpha and 1 beta. Okay. Now if I can define the alpha I prime, which is u alpha I times u dash. Okay. Some other matrix which is related to this alpha I by some unitary transformation. Okay. Now, then I check what is the relation that this alpha I prime satisfies. Alpha I prime, alpha j prime. I define my alpha I to be in this way, and if I try to check the commutation relation in terms of these prime alphas, what is the anti-commutation relation I find? Okay. So what I have to do, I have to just substitute the alpha i's here in terms of this relation. So it will look like something like this: U alpha I, alpha U dagger, another U alpha J, U dagger plus U alpha J U alpha J U dagger U alpha I U dagger. Okay, just substituted with the definition, and this U dagger U is a one identity, this U dagger U is identity. So what I am left with is this U inside the bracket. I have alpha I alpha J, alpha I alpha J plus alpha J alpha I times U dagger. Okay, but this is nothing but this is twice delta ij, right? Because alpha I alpha j satisfied twice delta ij. So this is nothing but U twice delta ij you should also consider the matrix. If these are matrix, you should also think of there is an identity matrix sitting here in that space. If this is a 4x4 matrix, then there is a 4x4 identity matrix sitting here, because this is not matrix. Okay, so this is delta ij times 4x4 identity matrix, and outside there is U dagger. So these U's are 4x4 matrices, right? Because they act on 4x4 matrix. These alpha i's are 4x4 matrix. This U acts on 4x4 matrix. Okay. If your alphas are 4x4 matrix, then the U has to be 4x4 matrix. Okay. Now we can take the twice delta ij outside U, because these are just simple number twice delta ij. For given ij, this is just some number 1 or 0. Okay. You can take this delta ij outside, and then you are left with just a minute. Then you are left with this U identity U dagger, which is again identity matrix, right? U dagger is identity. So U identity U dagger is also identity. So this alpha prime also satisfy the same commutation relation, anti-commutation relation, right? So if you can find one alpha I, by unitary transformation you can find another alpha I. So all those alpha i's which are related by unitary transformation are actually a solution of this thing, right? Is this okay? Hello?
Yes, sir.
Yes, sir.
So there is no unique solution, right? Two different solutions. If I find one solution, if you find one solution, then this two different solutions are actually unitarily equivalent to each other. Okay. I hope this is okay. So another possible choice for this alpha beta in 4th dimension is this, where beta is not. So one of the alpha is diagonal. For example, let me see. Yeah. Alpha I equal to, you can take, instead of doing the other, or the way that I did last time, the sigma to be in the off diagonal place, I put the sigma to be diagonal place, to be in the diagonal place. So minus sign, I need to check whether it will be here or just to be traceless. It should be something like this. Sorry. The upper I, lower I, all these things we'll try to distinguish in a couple of days. So this is alpha I. Let's say I make a choice of alpha I like this, okay? And you can check this alpha I, they will also satisfy the anti-commutation relation that just we verified for the other choice that we made, okay? And this is traceless. The minus sign is necessary, right, to make it traceless. And you can, I need to check whether it should be here or here, that you need to check, but I guess it's okay. And my beta is just not diagonal. By the way, not all of the alphas are diagonal. Which alpha is diagonal? Only one of them can be diagonal, right? So which one is diagonal here? In this basis? Earlier the basis that I choose is actually the basis in which beta is diagonal. Now I am choosing a basis in which another matrix is diagonal, but not the beta. But can you say which is this matrix that is diagonal in this basis? What is the matrix that is diagonal?
Alpha 3.
Alpha 3 is diagonal, because only out of all those sigmas, only sigma 3 is diagonal, right? So if I choose my alpha I to be in this way, alpha 3 will be only diagonal, and remaining two alphas, means alpha 1 and alpha 2 and beta, they are off diagonal, right? And this is perfectly valid. So this is also another basis in which you can solve this Dirac equation, and you can check that this particular choice and that other choice, okay, that I just wrote down, is connected by unitary transformation. Basically, this means the basis in which beta is diagonal and the basis in which alpha 3 is diagonal, they are related by unitary transformation. So they are unitarily equivalent to each other, and physics doesn't change under unitary transformation. Means if you work in a basis, two different bases in which the bases are connected by unitary transformation, you are doing the same physics. So they are not different. Okay. So this guarantees us that different solution will not give us different physics. So you are free to work with any one of these solutions, and that's the best thing, right? Means it should be like that. Otherwise, I can take this alpha and I will find one type of physics for a non-relativistic electron, and you can work with the other choice and you will get another type of physics for the relativistic electron. Right? This should not happen. It should not depend on the choice of alpha and beta. That is the statement. Okay. And this particular choice, this is very useful, this basis also, and perhaps we will work on this basis many times also, apart from the Dirac representation. This particular representation is called chiral representation or Weyl representation. Why it's chiral, why it's Weyl. Weyl is actually name of Hermann Weyl, but why it's chiral, it is actually he who found this basis. It's very useful in analysis of parity and many other things. So we'll see why this is called chiral basis or chiral representation. Okay. Representation, not I don't write the full thing. Yeah. Any question? So you have found in 4th dimension there are many choices for alpha beta. So you have at least found at least 2 such bases, and you can find many other such choices. Okay. There are Majorana bases, many other choices. There are infinitely many choices. So we found the solution for alpha beta. Now what you have to do? We have to go back to the Hamiltonian, means and see whether the physics that we will get from this thing is consistent or not. Right? This was one of the questions that someone already asked, and it's a perfectly valid question, so we should do that. Let me see if there anything here.
So this is the Weyl basis, right? Not the Dirac basis.
This is Weyl basis. W E Y L, I think.
And
The
Dirac
Dirac basis
basis
is
opposite of
beta was diagonal, identity minus identity in the diagonal, and these are up diagonal. Means sigma is over here and sigma is was here. Okay.
yes.
Yeah. Any other question? Okay. Yeah. Let me just find it. Few other stuff. Can you see this?
Yes, sir.
So, first of all, let's just check this probability density interpretation, right? This is one of the most important check that we should do. That what is the probability interpretation in this case and whether that is conserved or not. So this is my relativistic quantum mechanical equation, right? I H cross, so I assume that H cross is 1. I H cross del psi del t equal to H psi, or H is alpha dot p plus beta m, and alpha beta are given by this matrices. Beta is my this. By the way, here are some other notation is actually also there, but no, don't bother about that. I'll come to that. So my beta is this identity minus identity, and my alpha is actually 0 sigma I. Yeah, this is my choice. 0 sigma I, sigma I 0. Okay. So now if I just okay, what is that? If I now want to write down the equation, Dirac equation, okay. Just yeah, I think yeah, I found it. So the Dirac equation is basically Schrodinger equation, and which is just IH cross del psi del t equal to H psi. This is nothing but the Schrodinger equation, but the H is different. H is a relativistic Hamiltonian, but again it's completely different, has a different form compared to a relativistic Hamiltonian that we used to think of. Okay, it is linearized in P already. Okay, now if you write it explicitly in terms of the matrices itself, so if you substitute the alpha matrix and the beta matrix, how does it look like? It look like in this. It look like this. IH cross del psi del t. The H cross is missing because I assume it to be 1, and also the C I assume to be 1. So on this side you have a matrix. So on this side you should have a identity matrix. Right? There is nothing means that there is a matrix. Since these are 4x4 matrix, there should be a 4x4 identity matrix on this side. Otherwise the equation is not consistent. Okay. So what is this matrix? If you write down explicitly, it's M. So beta is diagonal. The choice that I am using is Dirac representation. So beta is diagonal. It's identity. Beta is this one. Identity 0, 0 minus identity. So if you just break that, it will look like this. M times identity minus M times identity. Alpha dot P will be just sigma dot P on the diagonal place, and another sigma dot P hat on the another off diagonal term. Okay. This is your equation, Dirac equation. Now the question is, what is psi? Is psi a single component thing or a multi-component thing? Means, okay, that is what we need not bother about so far, because all the equation that we considered so far was there was no matrix as such, right? In normal Schrodinger equation, there was a simple operator, differential operator acting on some function, and there is no need that this wave function has to be a matrix or column vector or a row vector. But now we have to bother about that, because here is something which is a matrix, and it's very usual that it will act on a matrix. Okay. it perfectly fine if this psi is not a matrix. If this is just a single component, one by one element of a. Okay. This psi is just a function, not a column vector, not a row vector. It's perfectly fine. But if that is so, you have to check whether this makes any sense or not, right? So if you just simply assume that this psi is not a 4 by 1 column vector, just simple 1 by 1 element means just a simple function, okay? It's not an array of function. Then how does this equation look like? It looks like 3 independent equation. Means if you just equate each component on the left hand and right hand side, you will find on this side what you have is this, okay? And on this side what you have is this, okay? If you multiply by psi, it will be all of them multiplied by psi, okay? This you can actually write it in a 2 by 2 format. This can be written as identity 2 by 2 matrix times del psi del t, and another identity matrix 2 by 2 identity matrix times del psi del t. This is equivalent to this thing actually. And on this side you have this same thing. Basically psi is multiplied with this, and with this. Because if psi is a single component thing, then it should be multiplied by all the elements, right? And then you equate both the sides, this side and this side. What do you get? You get 3 sets of equation. One is this, del psi del t equal to this thing equal to m times psi. Another equation you will get sigma dot p acting on psi equal to 0 from here. Another equation also sigma dot p hat acting on psi equal to 0. So these are same equation. Another equation you will get actually this multiplied by psi is identity times del psi del t equal to minus m psi. Okay. Now this equation doesn't have any t dependency, right? There is no del del t. So this equation doesn't give any dynamics. This 2 equation gives you dynamics because there is a del psi del t to it. But these 2 equation, to be consistent, simultaneously consistent to each other, the only choice is m equal to 0, right? Because del psi del t cannot be some positive quantity times psi or again some negative quantity times psi. You can just add these 2 equations and you will see that del psi del t is 0. So basically psi is a constant of motion, means it's independent of t. And this is a very trivial equation. There is no time evolution of psi, right? So if you assume that psi is a single component object, then there is no dynamics of psi. There is no time evolution of psi. But this is what we wanted. Means in quantum mechanics also something like classical mechanics, right? Where we solve the dynamics, means we solve the time evolution of the system. But if you assume that psi is a single component thing, there is no time evolution of psi. Okay, and it's a very trivial set of equation. So what is the other possibility which will give you non-trivial thing? The thing that is possible is actually psi is not a single component thing. Then psi, what can be the psi cannot be a 2 component object, it has to be a 4 component object because there is a 4 by 4 matrix, and a 4 by 4 matrix can only act on a 4 component object, right? Then only this equation will be consistent equation. So in order that you don't have a trivial solution, psi has a dynamics and this equation makes sense, psi at best be a 4 component object. Okay. So now we have a completely different thing, means earlier, so far whatever you have done in quantum mechanics, you have seen that psi is just a wave function which is a single component object. But in order that the Dirac equation has to be a consistent equation, mathematical equation, psi that appears in this equation has to be a 4 component object. Because all these matrices are 4 by 4 matrices, alpha and beta. Okay. So this actually psi is 4 component, and there will be 4 such equations that you can find for each component. Okay, there will be one equation for del psi 1 del t. If the psi is a 4 by 4 object, it will be del psi 1 del t, del psi 2 del t, del psi 3 del t, del psi 4 del t. So there will be 4 such equations for each of these components, and we will find those equations and try to solve them later on. But this is why this psi has to be 4 component thing. Okay, is this okay?
Yes, sir.
Yes, sir.
Okay, now let's check the and this is where actually I warned you last time. Then when you try to check this continuity equation or the conservation of rho and so on, you should be careful of multiplying by psi and psi star and psi dagger, whatever you want. Okay, because if psi is a 4-component object, 4-component column vector, then psi dagger will be a 4-component row vector. Okay, so they do not commute with each other. Okay, so you cannot do it in a different arbitrary order. So you have to be careful. So now I do that. So I have this equation. Okay, basically the equation should look like this. Psi is a 4-component object. So it has 4 components, and I just name this 4 component to be psi 1, psi 2, psi 3, and psi 4. So this is a 4-component vector, and this is acted by a 4x4 matrix. That's it. And on this side you have identity times there is identity matrix times a psi, which is a 4-component object, psi 1, psi 2, psi 3, psi 4. And if I act by identity on this psi 1, psi 2, psi 3, psi 4, you will get something like this. Okay. Okay, so now I take this equation, Dirac equation, which is I h cross del psi del t equal to alpha dot p plus b times psi, and I now take the Hermitian adjoint. But this is by Hermitian adjoint, I mean by just take Hermitian adjoint in this 4x4 matrix space. Okay, means I just, or one way could have been I just write it in the component form, all this equation, and then just take complex conjugate. That is also fine. But yeah, I just want to take the Hermitian dagger in the 4x4 matrix space. So what I do, I just take the adjoint of this equation. So this will be del psi dagger del t. There is a also, okay, by the way, I just also use the coordinate basis of this equation. This is in any particular it's basis independent representation. This is in coordinate representation of Dirac equation. This p will be just simply minus IH cross grad operator, and if I just take the dagger of this, it should be plus I gradient of psi dagger, okay, dot alpha. This order will interchange because psi is a column vector and alpha is a matrix. If you take dagger, it will be a row vector on this side and matrix will be on this side. The same is true for this. This will be psi dagger b time. Okay. So this is your equation for psi. This is your equation for psi dagger. If you multiply this equation by psi dagger from left, and this equation, because this is equation of psi dagger, and psi dagger is a row vector, so you can only multiply this equation by psi from right, not from left. Okay, so that's why this order matter. And if you do that and subtract, you will get psi dagger del psi del t plus del psi dagger del t psi equal to something like this. And this is a very nice expression, right? You can take del t common, it will be psi dagger psi, and it's like our old interpretation of probability, right? Psi star psi. There was psi star psi earlier because there was only 1 component. Now we have 4 components, so it should be psi dagger psi. Basically, this means psi 1 square mod psi 1 square plus mod psi 2 square plus mod psi 3 square plus mod psi 4 square. Okay. So there are 4 components. So basically, mod square of each of them, sum of mod square of each of them. So this is psi dagger psi. So we have to show that if we interpret this as our probability density, then it will be conserved. That we have to interpret. But let's check the continuity equation. So this is your continuity equation. So this is del t of, if you call this thing to be rho, so this is del rho del t, and this is your minus gradient of this thing. And if you call this your j, the j is slightly different. Earlier j has a special derivative, right? But now there is no special derivative of j because the equation is actually linear in the derivative. Earlier the special derivative was second power, second order derivative. Now we have a linear derivative, so there is no derivative in the current. And this rho is perfectly fine. There is no del t extra in the definition of rho because now we are working with linear derivative in time, means the first order derivative in time, not second order derivative in time. If you have second order derivative in time, again you will have the problem of non-positivity of the probability density. Okay. So this is your continuity equation. So you can interpret this is your probability density and this is your probability current. We'll derive this relation again from a different context, from a symmetry principle later on, that this is a consequence of a global continuous symmetry, this conservation thing. Now you can just integrate this equation throughout space, whole space over d cube x, and then take this term to the boundary and set it to 0. You will see that the ddt of total probability density will be 0. That means the total probability will be conserved, and this is your probability density, and it's integrated over full volume will be conserved. So that the problem that we are facing in relativity was about this positive definiteness of the probability density has been cured in this Dirac equation, right? But there are other things that you should also check. What are the solution, whether the solution has any physical meaning or not, and so on. And we'll do that in the next class, okay? So we'll stop at this point. But it has this nice feature that the probability density interpretation is there, and it is positive definite, and it is conserved, which should be true if it's a means quantum mechanical system. Okay. Any question?
Sir,
Hello?
what are the components of psi?
The
Components of psi.
components of psi means explicit form you are trying to say?
Yes, we are accustomed to scalar functions.
Yeah. Yes, each of this is a single component thing. Psi 1 is a single component, it's a scalar function. Psi 2 is a scalar function. Psi 3 is a scalar function. Psi 4 is also a scalar function. And this is a collection of 4 objects, which is a 4 component object. If you want to see what is your Psi 1, what is this scalar function, you have to solve this equation, right? Unless you solve this equation, you will not be able to tell that, right? So we'll solve this equation next time.
So
Is
each
that
of
okay?
these psis
Yeah.
are a solution of Dirac equation, which in turn gives
This is
us.
a Dirac equation. This is a matrix equation, and each of this psi is a solution of a equation which actually you can find from this, right? You can find the equation for each component, right? You have to multiply this
Exactly.
matrix with this vector, and then you equate. So you will get another. So this side will be equivalent to another column vector, right? Then you equate this column entry of this column vector on the left hand side with the first entry of the column vector that you get by multiplying these two on the right hand side. And each of this will be a separate equation. There will be 4 such equations, and they will be you need to solve those 4 equations to get the psi 1, psi 2, and psi 3 and psi 4. But they will be coupled equation. You can already see, right? Because this is a matrix which mixes this psi 1, psi 2, and psi 3, psi 4, right? So equation of psi 1 will be mixed with psi 2, psi 3, and psi 4. I can show you that actually for one particular.
My question was that each of these elements, like psi 1, psi 2, psi 3, and psi 4, it denotes the solution to my equation, right? A different four solutions to my equation.
Yes, I should have 4 solutions to my equation, exactly.
So what is the physical interpretation of these each and every solution? I mean, psi represents something. So psi is.
There. So, for example, I can maybe let me just let me not wait you maybe. Let me just explain at least this thing in one particular example. Okay, that will be, I guess, helpful for you. But to interpret this solution, we need to do a little bit of work. Okay. You see, all that this equation that you got is not a decoupled equation. It's a coupled equation. Means equation of psi 1, del psi 1, del t will not only have psi 1, it will also have psi 3 and psi 4 and psi 2.
Exactly.
To solve psi 1, you need to know psi 2 and psi 3 and psi 4. But to solve psi 2 and psi 3, psi 4, you need others also, right? So it's a coupled equation. It's not straightforward to solve, but it can be solved. So we'll do that anyway. But what is the simple strategy you can adopt to solve it? The simple strategy you can adopt to solve it, you can go to the rest frame of the particle, because this is a massive particle, so you can go to the rest frame. In the rest frame of the particle, the momentum is 0, right? So this P will be 0 actually in the rest frame of the particle. So this term will drop out. So the equation will look like del psi del t equal to beta m psi. And beta is diagonal already, right? It has identity matrices. So then it will be a decoupled equation. All these psi will not talk with each other. So let me just show you that. Yeah. If you go to the in a rest frame of the particle, the equation, Dirac equation will become like simply like this: IH cross del psi del t equal to beta m psi, and beta is diagonal. So if you multiply by beta this side, it will be only just m psi 1, m psi 2 minus m psi 3 minus m psi 4, and these are the 4 equations that you have for each of these components. On each of these components is a scalar function now. So del psi 1 del t is m psi 1, del psi 2 del t is m psi 2, del psi 3 del t is m minus m psi 3, and so on. And the solution of this equation are just the exponential solution, right? Psi 1, psi 2 will be some coefficient times e to the power minus int, and psi 3, psi 4 will be some coefficient times e to the power plus int. Okay. So these are the solution for each of these component. And what is the interpretation of this solution? So one of the interpretation, first of all, that you can see is this: you can just operate this IH cross del del t, right, on this operator, on this wave function, and you will see that that should give you the energy eigenvalue, and the energy eigenvalue for this solution is E equal to plus m, and that is consistent because E square is square root of E is actually square root of P square plus m square, right? If P is 0 because you are in the rest frame, then E can be at least plus minus m, right? Because it is E square is square, P square plus m square, so E is plus square root of plus minus square root of P square plus m square, and if your P is 0, then it can be plus minus m only, right? In classical mechanics, you discard the negative energy solution, but here you have to be careful whether you can discard the negative energy solution or not. The first two of them are actually positive energy solution with E equal to plus m, and the remaining two is actually negative energy solution with E equal to minus m. The question is what to do with the negative energy solution. Whether you can discard them. If we discard them, in quantum mechanics, you know the problem is there is a completeness relation. If you work with a subset of solution, then the solution, the remaining solution may not form a complete set of bases, right? Any arbitrary state cannot be expanded in terms of this basis, which is not complete. So you have to work with the full basis, all this solution. Then only this completeness relation hold, and then only you can expand any arbitrary state in terms of complete set of basis is all this solution. And if you want to, and for that you need to keep this negative energy solution also. And this is very intricate with this, very intertwined with the relativity. If you are in a relativistic domain, the negative energy solution is bound to be there. And in fact, it is not a problem of the theory; it's actually a cure of the theory. And we will see what it cures and what it predicts. All these things we'll see in future classes. Okay, but that's it. That it has this negative energy solution as well as the positive energy solution, which you have. So far in quantum mechanics, we have only found positive energy solution, right? For a free particle cannot have negative energy at least, right? For if a particle in a bound state can have negative energy, but to have a negative energy for a free particle is something which is weird, but it's there in relativity, right? A free particle has negative energy in its rest frame. So you have to see what is the meaning of this, how to interpret this solution, and so on. Okay. Any question? And then also you need to. So there are two solutions. Just a minute. There are two solutions, psi 1 and psi 2. Both of them have same energy. So what does this two solution means then? What is psi 1? What is psi 2 actually? Means both of them are actually have same energy. So these are degenerate solution with same energy eigenvalue. But is there any further distinction that you can make for this? The answer is yes, and we will do that in the next class, not in this class. Yeah, go ahead.
Hello, sir.
Yeah.
What is the importance of chiral representation? You said alpha 3 is diagonal.
I'll come to that when I will be discussing chiral representation. Okay.
And now we did the Dirac equation.
By
the
the way,
basis
just a moment.
beta diagonal.
Exactly. Very good point. Yeah. So you see the solution, sorry, the property that you have found for the alpha beta, these are representation independent property. So this fundamental property, right, these are or defining property that should be satisfied by any alpha beta. But now to find the express solution, we need some basis, right? And this solution that I found is actually in the basis in which beta is diagonal. That is in the Dirac basis, not in the chiral basis. If I work in a chiral basis, then beta will be off diagonal, and again this equation will be coupled equation, even if I am in a rest frame. So I'll actually give this as an exercise to solve this equation in the rest frame for off diagonal beta, that is in the chiral basis. So they are already in the assignment. So I'll give it to you, but it's not very difficult. But again, the solution is actually basis dependent solution, means it's in a particular basis. The solution might look different in a different basis, but the physical meaning or physical, what is physical is actually the expectation value of the observable. Those things will be basis independent anyway. Okay, that is you know already, right, in the quantum mechanics, because for the wave function you can go to any basis which is related by unitary transformation, right? And in various unitary transformation, the wave function may look different, but the expectation value of observable quantities will remain same. Okay. So this is still in this case also. So the solution that we got is in a particular basis, and it's actually in the Dirac basis. Okay.
And what are the boundary conditions that we have to apply to get the solution? I mean, xi.
Yeah, the boundary condition you can apply to get the to fix the coefficient. Okay, but this coefficient can be fixed by normalization also, right? Because right now you see in the rest there is no x dependency that you can apply that at x tends to 0 it will be 0 or not. There is no x dependency, right? Because the x dependency of this equation is gone if you are doing it in a rest. Right?
Hello. Hello. Hello.
Can you hear me?
Your voice is fading in and out. Can you please repeat?
Because the network, let it be there again, means let it be restored again. Can you hear me right now?
Okay now. Yes, sir. It's okay.
Yeah, yeah. So what I'm saying, so this equation is actually valid all over space-time, right? Because there is no gradient dependency here, right? There is no x dependency here.
Exactly.
This is in the rest frame, but the frame can be anywhere in space. So this solution is actually true at all space-time point. Okay. And this coefficient can be fixed by normalization, right? If I normalize my phi, I can fix this coefficient. Okay. But what I actually didn't explain is this: there are still two solutions for each of these E. For a positive, there are two positive energy solution, two negative energy solution. So basically, these are degenerate solution, right, with same energy. So how can you distinguish these two solutions further? The answer will be the spin of this thing. So one of them will be positive energy spin up solution, positive energy spin down solution, and another will be negative energy spin up solution, negative energy spin down solution. But how the spin enters in this picture, this we need to discuss next time. Okay.
Okay. So is this the manifestation of losing the p going to the rest frame, or I mean, having a degenerate solution?
Sorry?
Is this the manifestation of going to the rest frame that we are getting a degenerate solution?
No. This degenerate solution will be always there, even in rest frame, even if you are in a moving frame. Okay, means in which the particle is in a frame in which the particle is moving. We will always have 4 independent solutions, and there will be 2 of them will be always degenerate. Okay, this is always true.
And if we don't consider our Dirac basis, we consider Weyl basis, then it will be dependent on my position, right? We will have a sigma dot p, and then there will be a derivative on the right hand side to solve.
There will be actually means momentum dependence, you can say, because we will be solving it, I guess, in a basis in which in a momentum basis. So there will be a momentum dependence.
So in this case, we can solve for C's by using normalization condition. But in that case, we can also have the second, if we want to solve, if there might be a second kind of solution where we can have a boundary conditions that can help us solve in Weyl basis.
Yeah, we'll see that. But the answer is actually you will not require any boundary condition. For example, when you solve a free particle equation in normal quantum mechanics, there is no potential anywhere. You can check that means you have this e to the power I k dot x type of solution, right?
Yes, yes.
And there is a normalization to it. Means what else you need to fix there? Means there is nothing, I think. Right? It's an exponential solution. It doesn't vanishes at the boundary, right? As such.
This is a free particle solution, so we don't have.
Yeah, free particle solution. Yeah.
So we don't have any boundaries. So no boundary values.
There is no boundary, exactly. Because we are also doing the same free particle case. So there is no boundary as such, right?
Exactly. Okay. Yeah.
So that part is exactly same here. Okay.
Okay.
Okay. So we'll stop today here and we'll pick up from here. Okay. Next time. Any question? Any other question? Okay. So let me stop this thing.
So if there are no questions, I will end this meeting then. Oh, sir is already.